So, welcome to the last energy lunch of the year in this, our 6th year. In October, we passed the 5-year mark. We're now in our 6th year. It might interest you that the energy lunch has brought more than 60 speakers to Jefferson County over those 5 years plus, and they've come from as far away as many of you already know, from Wilpolstried, Bavaria in Germany. That was our program, I think, in September, or maybe it was August. At any rate, we thank everybody for your presence and for your support. It's obvious to me that if there's ever going to be a true impact on this country's energy use, it's going to have to happen here at the local level. And I really believe that this is the time and this is the community for that to happen. And we've got a speaker today that's going to help us understand how we can actually make that a reality. But first, I want to recognize all of our sponsors who most of you know, but Power Trip Energy, neither Andy nor Jeff Randall could be here today, but they've been stalwarts. Sunshine Propane, of course, Robert Urish is here with us. Huber's Inn, and I saw Letitia someplace. There she is, right there. Alaska Power and Telephone, Bob Grimm. Port Townsend, Steve Tucker, newly reelected. We're very thankful for that. Frederickson Electric, and I haven't seen Hans, but they've been great supporters over the years. Frederickson Electric, the Port Townsend Paper Company. Often Kevin Scott is here with us. I don't see him today. The Washington State Department of Commerce has become a sponsor, as well as Ravenna Capital Management. What I'm going to do now is I'm going to introduce one of the principles of CountyEnergy.us. And Dana Lee and Rick Van Auken are the two guys that really, really do make this happen. And I've mentioned them before. We're fortunate today to have Dana here with us, and I'm going to introduce Dana, who will give you a little background and introduce our speaker for today. So let's hear it for Dana Lee.
Thank you, Larry. Great to be here with you. I come to these about once a quarter, and every time I learn something new and exciting. Based on what I have heard speakers say in 5 years, based on what I have heard you say, with feedback from sponsors and those who participate in the planning and thought process that goes into where should we take our energy future, I think that it's time for the combined forces in this room and outside this room to emulate what you heard from Günter Mergele and the emissary from Wilpolstried, and organize yourselves to plan. We now know enough of things that we could do, of things that we should do, of things that we shouldn't do, or things that will never work, to be able to sit down together as a community and put together a comprehensive energy plan for the future. That's what they did in Wilpolstried. Now, they were very fortunate. They had one governmental entity, the village. We have the city, the county, the port, the PUD, Robert and his peers in the liquid energy supply business. It's much more complex. It will not be an easy thing to do, but by doing so, you'll set a course that goes from being piecemeal, where someone sees an example on the internet of a wonderful thing that was done in Norway or where have you, and you see them posted on the listserv, and we converse about that, but we don't integrate this into a plan. We've got to have a plan. So I encourage you to plan. The next time I'm back here in a couple of months, hopefully that has been formalized in some way. Now, without taking any more time from Dr. Steve, I went to the Argonne National Laboratory. Never been to a national laboratory before. It's outside Chicago for the Ammonia Fuel Association conference in September. And in a bit of serendipity, Steve Wittry was presenting. And I listened to his presentation and I said to myself, this is an idea that needs to be told to the folks in Jefferson County. And I'm not going to be the one to tell them, because I could begin to outline the picture for you, but here comes our expert. Steve will tell you a little bit about his background, how he came to be passionate about a non-carbon fuel. He's a member of the board of directors of the Ammonia Fuel Association and currently aligned with the Clean Air Task Force. I know carbon is on all our minds, and as we think about the effects of Paris and the plans to decarbonize, you're going to hear a way that we might begin doing that at this level. So without further ado, Dr. Steve Wittry.
Yeah, I'm Steve Wittry. Been in the energy industry since 1980. I got my PhD and joined Amoco, and then worked for BP. So I was in the oil industry for 30 years. My last 6 or 7 years with BP, I was the director of advanced technologies for BP. So worked on the things that we were going to, and did work a lot on the technologies and the fuels and the energy services that were beyond petroleum. I joined BP as we were bought by BP as Amoco in 1999. And that was the year after John Brown gave his Stanford speech that broke from the oil industry and said that we need to start to think about these things and invest in them and that sort of thing. So that was also the year that the analysts were very nervous and asking us why we were talking about we were beyond petroleum, and how are we going to continue to make money if we don't pay attention to the real business we're in and all that sort of thing. So I was actually one of the two first people that was asked to start to put together the strategy for how we needed to think about and structure the strategy and capabilities toward that end. And spent the next 10 years doing a lot of that type of thing, including in China and Russia, and a lot of time in London. I got to know London very well. And basically, so that was across the whole piece. So I learned a lot about, I learned a little about a lot of things. A mile wide and an inch deep, and some places 10 feet deep. But sort of everything that came into the board about ideas from the outside, and what about this invention and that kind of thing. I saw a lot of that. I worked a lot in China and technologies there, and low carbon technologies, and sort of very different society and economic system. How do things work there versus here, versus in Russia, versus in Europe. And so got really a chance to do a lot of thinking and analysis on what works and what doesn't, and why not and why, and that kind of thing. I retired about 4 years ago and joined the Clean Air Task Force, which is an NGO based in Boston, nonprofit. Clean Air Task Force had its beginning 20 years ago, and working on coal plant emissions and sulfur oxide emissions, and the first and only to date working actually cap and trade system, which was SOX trading. So works with the government and industry, takes donations from neither, so it's kind of foundations and high net worth individuals that are interested in that sort of thing. So stays as pristine as possible in that kind of environment. So a very different environment for working in a big oil company, but working on many of the same things actually. They had a very high interest and still do in U.S.-China cooperation on new technologies and commercialization of technologies in both countries, and a lot of different ideas come from both, and both have different capabilities and that sort of thing. But I guess one thing to say here, just as part of my introduction, is I'm not here to sell anything, so I don't have any patents or anything that is kind of gonna if you accept my proposition and we start to build something here, I get a 5% cut or something like that. That's not what I'm about. Basically what I'm about is still continuing to do the things I've done for my life's work of looking at and developing options for the clean energy technologies that will work, and by working meaning that they have a chance to grow and flourish and really be practical technologies, not necessarily without subsidies, but with in sort of a reasonable economic framework. Every energy technology gets subsidies or whatever, but things that will work that aren't kind of wildly more expensive or sort of take resources that once you get a 0.5% penetration become much more expensive, or you run out of them, or things like that. So I look at solutions that come forward that that might be developed in the whole framework of the ecology of what's going to be needed in new energy technologies, and a lot of what's going to happen there is systems. So, a technology from over here, a biotechnology thing with a new engine or whatever. There's lots of things that are developing in many different areas, and you can develop useful solutions with that. So, with that said, I came upon ammonia after I left BP. And as basically a zero carbon fuel. So for, if you're not familiar with ammonia, ammonia is NH3. It has nitrogen and 3 hydrogens rather than methane, which has a carbon and 4 hydrogens. If you burn any of the hydrocarbons, gasoline or methane or natural gas or LPG here or coal or whatever, the natural end product of that is CO2 and hydrogen. And CO2 is the gas that we're worried about as a greenhouse gas. And when people say you want to come to a low carbon economy or whatever, that's what they mean. You don't burn things that have carbon atoms in the fuel. And you can either do that through like nuclear, which doesn't burn anything, or hydroelectric, which if you got nice dams around and stuff like that, the water evaporates and goes back to the top of the dam. You got nice, convenient solar energy, or solar energy, or those things. But in general, if you're burning things, you're burning stuff that has carbon in it, even if it's biofuels. To some extent, you pay that back by grabbing some CO2 out. But it's that's basically a natural consequence of that. And so we spent a lot of time, scratching our heads about, for instance, zero carbon transportation fuels or low carbon transportation fuels. And there you get the fuel cells and batteries and biofuels and that kind of thing. And so that was big part of the strategy, and we spent and are still spending a lot of money on advanced biofuels and BP. But it never occurred to me or to my colleagues or anybody, what's other stuff you could burn that doesn't have, carbon in it? Because, you get into exotics very quickly with that, and, it's hard enough to try to think about, how you introduce ethanol into fuel, which is, very close and, very familiar technology. Much less something that's kind of strange and is not built on a carbon framework and, silica or something like that, which is sand. You don't think about that. And so, ammonia honestly never, in a very natural way, doesn't occur to people that grew up in the hydrocarbon industry for sure. Nor does it, kind of appear to people that didn't grow up in the hydrocarbon industry because they don't know fuels and don't think about engines and, that kind of thing. So kind of doesn't come up. When I was back here working in some areas, I met a guy from, actually from the Clinton Global Initiative that was mentioned, he was working with some people on ammonia fuel. And, I thought about that, and first things that come up was, well, why would you want to burn fertilizer? And, thinking about that, and, it must make a lot of NOx, it must make a lot of, nitrous oxides and that kind of thing. But, looking at it over the last 3 years, actually, there aren't any barriers that one can come up with that aren't relatively easily addressed. There are people that have been working on this for 10 or 12 years. The Ammonia Fuel Association, which Dana mentioned, is a group that's, this was their 13th meeting, 12th or 13th annual meeting, I think. And, so I went to that meeting and got to know these guys. And, we'll talk a little bit about this, but then I'm going to talk about the neighborhood energy stations. Essentially, in terms of the things that come up as sort of the natural questions is, do you get NOx when you burn it? Basically, the answer to that is you don't. It's the same mechanism that you get NOx if you burn natural gas or diesel or anything. It's basically just high temperatures. So the bottom of the thermodynamic hill, when you actually just burn ammonia, is nitrogen and water, and you can get a little bit of NOx, just like you can get a little bit of NOx from methane engines or anything like that. And if you do, you can clean it up in the same way you clean it up in hydrocarbon engines with a process called SCR, where you actually put in a little bit of ammonia and react it with the NOx, and they knock each other out and make nitrogen and water. So, sorry, I got a question back there.
Could you explain what you're talking about, what NOx is?
Oh, sorry, what NOx is, all right. Right, okay, good. If you've read about how embarrassed Volkswagen is about, their NOx from the emissions from their engines. NOx is NO2, NO3, N2O3, N2O. It's basically, when you get higher temperatures and you've got nitrogen molecules, N2, and you got oxygen molecules, O2, when you get to higher temperatures, you get enough energy that you can get some of them to react together so that nitrogen and oxygen will react with each other and make a small amount, usually parts per million, of these things that are called NOx. And, NOx just comes from NO, X, which means the stoichiometry is, just kind of, there's a bunch of them. But, it also means noxious and all that kind of stuff. So it's, kind of serves the double purpose as that name. NOx is a very definite air pollutant. It's a precursor to smog. It's a precursor to ozone. It's not the kind of stuff that you want to have coming out of your cars or your power plants. particularly in urban areas and that sort of thing. The reason that Volkswagen has had a problem, and frankly, all of them do, I'm sure, but they maybe weren't quite as egregious as Volkswagen, is you can tune engines that aren't kind of running hot, or you trying to rabbit start or whatever. When they're running in normal mode, they're not very hot, so they're not making as much NOx. But when you jump on the gas pedal or whatever, you run them hot for a while, and that makes more NOx. And so the way things are set up with the controls on what you do in the after treatment and that kind of thing, we're supposed to kind of tamp all that down, and it's supposed to make the car less peppy and that kind of thing, or does if you actually run it right. And they had set up to run their engines so the engines would know when they were actually being on a test stand, and the steering wheel's not being turned or something like that. So they could cheat the test to keep from making the NOx when supposedly it was supposed to make it, and that was kind of how they got around that. But the basic trade-off is in a diesel car for this is, if you want peppy performance and good acceleration and 0 to 60 performance and that kind of thing, you have to give that up and there's not much way to get around it if you want to have low NOx production in terms of so these are the kinds of trade-offs you get into with these things, or with an ammonia engine, or with an integrated internal combustion engine. In general, the kinds of trade-offs that you get into in any case, and ammonia is not different than that, even though it does have a nitrogen in the fuel. In general, what comes out, and there are people that we're working with that are running advanced engines that basically have undetectable nitrogen oxide production through most of the range of how you would operate. The other kinds of stuff that comes out of hydrocarbon engines, like black smoke from diesel and CO and sulfur and that kind of thing, you don't have any of that. So essentially, in that ideal case, and it is an ideal case because there's possible to get some NOx, but in that ideal case, you could just run that emissions directly into your living room, and it would be a humidifier basically. But it's nitrogen and water, so it's very clean from that point of view. It's also very clean in the environment that you run it in, because you have no CO2 emissions there. Now, the way ammonia is made in large-scale manufacture right now, it's made from natural gas, and you do get CO2 emissions from making that. So people now call that brown ammonia versus green ammonia if you make it with no CO2 emissions. There are ways to do that. A couple of the kinds of things that we're looking at is when you make ammonia from natural gas, the majority of the carbons that go into the process, that's the front end for making the hydrogen, the majority of that comes out as pure CO2, which we used to call it sequestration ready. When it doesn't come, the point is it doesn't come out as flue gas, which is when you use it in a power plant, it's 15% CO2 and the rest nitrogen, and it's extremely expensive to kind of pull that out of the nitrogen, so that's what's called the carbon capture part. So there's very low-cost sequestration options available for that. And there's a lot of things back and forth about whether sequestration is going to work or not. But essentially, if you're pulling natural gas out of the ground, you're making a hole that has pore space that you can put CO2 back into. So in terms of the CCS options that are available, this might be one where you could take the low-cost CO2 that's being developed in lots of places, Alberta, Pennsylvania, Texas or whatever, strip out the energy, strip out the carbon, and put the carbon back in the ground, and come out with a fuel that goes down the line and is basically a zero carbon fuel. The other aspect of that, or the other thing you can do, and actually the way the first kind of Haber-Bosch plants were run, is hydrolysis of the water. So if you've got a lot of hydropower here, and actually those are the first ones in Norway, they used hydropower to run electrolyzers to split water. It takes a lot of energy to split the H2O into H2 and O2, but it's kind of a chemistry lab demonstration that the teachers do. You have a battery and you got two electrodes and the bubbles come up, and you can put it in a balloon and you put a match to the balloon and it pops, and that kind of that's essentially what it is. It's more expensive to make ammonia that way because you've made the hydrogen, then you can pull the nitrogen out of the air, and you do all the catalysis and the heating and that kind of thing. That's a more expensive way to make ammonia. But it's not wildly more expensive. It's something that was practiced before actually the natural gas things. The costs will come down over time, and to the extent that we want to use low-cost hydropower or low-cost overnight nuclear, or low cost, we got a wind farm that's making, too many megawatts 30% of the time or whatever, with very low cost electricity. Those are things that you can do to get to green ammonia as well. Sorry, yes?
If electrolysis of water, you get hydrogen and oxygen, how do you get nitrogen or ammonia out of that?
Okay. The main cost and the main energy cost, really, of getting the two things that go into ammonia is, as you say, you need the nitrogen. So the air is 90% nitrogen, or 80% nitrogen, sorry. And in large plants, it's basically cryogenic, so big refrigerators that separate and distill the oxygen from the nitrogen. There's a process that you would use at sort of medium scale. It's called pressure swing absorption, where you have absorbers that preferentially capture the oxygen, and then pure nitrogen comes through. So you can get pure enough nitrogen from that. And then you sort of heat them up and run the oxygen off another way and that kind of thing. So that's a way at smaller scale that you can economically separate out the nitrogen. Then you have nitrogen and hydrogen, and if you got a use for the oxygen and somebody wants some pure oxygen, which a lot of people run things to make pure oxygen, you can sell that as a byproduct. And then with the nitrogen and the hydrogen, basically after that you need a kind of an iron catalyst, which is not an expensive catalyst. You need 200 atmospheres of pressure, so you need lots of pressure, and you need 400 centigrade, so that's more than cooking a turkey, but it's a lot less than a lot of chemical processes you run. So it's there's nothing that's exotic about doing it. It's just that over time and economy of scale and availability of energy and the processes to develop, it's cheaper to do it right now with natural gas. There's no question. But again, if you've got very low cost power, if you're thinking about running your hydrogen economy from from wind and solar and that kind of thing, this is not more expensive than doing that. As a matter of fact, this may be the best way to do your hydrogen economy, because once you got your hydrogen, you might want to, combine it with nitrogen and make ammonia, because that's a lot easier to store and that's a lot easier to move around. Ammonia, we know how to move around. Ammonia is the second most produced chemical in the world, actually, because of the fertilizer. Probably half the nitrogen atoms in your body have gone through a Haber-Bosch plant, because they have. I mean, that's where the fertilizer comes from. If we didn't have the Haber-Bosch process, we'd support about 20% of the world's population right now. So It's already a critical part of, the world's ecosystem of chemical processes. And, it moves around like LPG. So here in this community, you're used to LPG. A lot of what you do is LPG in terms of, delivery and, storage of energy and things like that. And the reason you don't do, cheap methane, even though you're close to Alberta and lots of things, is it's expensive to build pipelines out here. You can't build storage for, you can. It's very expensive to build storage for natural gas. So ammonia is pretty much it looks pretty much the way that LPG infrastructure looks. It's, tanks with kind of bicycle tire pressure type of pressures. It has its own set of, toxicity and safety hazards, but it's safer than LPG. If you knock the valve off in an LPG tank, you can get a heavier than air cloud that goes out and hits a spark somewhere and causes a big explosion. If you do the same thing with an ammonia tank, it's lighter than air and it dissipates, and people smell it at kind of 1% of the explosion limit and that kind of thing. So the point is that every fuel, by definition, has a lot of energy in one place. That's the point of having a fuel. And so they will all have scenarios where you can say, yes, I could kill myself if I drink it or spray it in my face, or fill my house up with it and light a match or whatever. And those are things that will just have to be handled. But ammonia is something that is, shipped all over the place. It's stored all over the Midwest. Actually, when farmers in the cornfields in the Midwest apply ammonia, it's just little spigots that are open spigots that go 2 inches down into the ground, and they blow the ammonia out through that. It's not it's something you have to handle, but something you can go forward with. Okay, so I haven't even gotten to the first slide yet, but basically that was all background. Chemistry and fuel lesson. But as I was going through this, and thinking about where might this be most useful, one could certainly think that transportation. It's a zero carbon transportation fuel. If you run your ammonia trucks and ammonia diesel engines and that kind of thing, and provides a solution to the problem that you can't do carbon capture on gasoline engines or CNG or whatever. And so if you can make green ammonia and if you have ammonia trucks, you can do that. And then, so in Belgium in World War II, they actually ran their buses on ammonia because they didn't have hydrocarbons. You can do that. It's not the most efficient, and of course you have to actually tune engines to do these things and that sort of thing. But actually, engines for transportation, those are much harder and take much longer than things that sit on the ground and just make electricity. This is a lot of experience out of the oil industry and out of the gas industry and that kind of thing. If you want to get a new fuel component, even a component of gasoline, like say ethanol or whatever, approved, it's years and years of regulatory stuff. It's very naturally it's things of what happens in retail interface, and when customers are exposed to this or spray it out in the accidentally on the forecourt, and and in a small engine that's running all different kinds of weather and goes 80 miles an hour down the road, and what happens to the tank when you have an accident and all that kind of thing. You don't have to deal with all those problems if you're talking about actually stationary power generation. And stationary power generation is, a source of, a great deal of the CO2 that we put out to even natural gas power stations, certainly coal power stations. And, something that I learned as I was into this, that actually the sales of diesel gensets around the world, so the diesel, just like you rent in True Value or whatever, or buy, but up to kind of megawatts. The sales of capacity of diesel gensets every year is 60 gigawatts of capacity. And for people that aren't calibrated to that, a gigawatt of capacity is about a nuclear power plant. So, there are lots of places in the world, not so many places in the U.S. that use diesel gensets anymore because you can't burn diesel anywhere pretty much. But there are lots of places in the world that really depend on, on diesel gensets. So if you have, ammonia at $300 a ton, which is something that you could do if you were, building your own project and, had, access to the gas and that kind of thing. You make money selling $300 a ton ammonia for energy. That's equivalent to $2 a gallon diesel in terms of the energy content. So, this is something that for, kind of rest of the world and for people that are like in Hawaii using diesel gensets or, the Caribbean where the islands are too small for LNG. This is something that has natural applications already. It is a liquid fuel, so it's something that can be moved around, and you guys are used to seeing that moved around like that. So how did I get to neighborhood energy stations? I live in the Loop in Chicago, so right next to 9th and State. So we have a nice little sort of enclosed neighborhood that's mostly, two-story townhouses, but it's the only place like that within a 5-mile radius. The rest of it is 40-story, condos and that sort of thing. You look at that as, real opportunities for combined heat and power, for instance. And you look at cities, particularly if you spend time in New York or, Beijing, or a lot of places that, kind of are right at the edge of whether the grid can really provide power through the winter through a polar vortex, or, if a transmission line falls down that's going into Brooklyn to sort of the end of the line or whatever, where, there's a real particular problem with, or risk that, your power can be out for days and days. And, I think that's something in discussions I've had here that people worry about here as well. And so a lot of what people that are looking at, the future of energy in the U.S. right now, and DOE and, the people that are certainly looking at low carbon energy also spend a lot of time awake at night about energy security and, security of the grid and that kind of thing. And in that case, people talk about microgrids. So, generators or battery banks or whatever that are kind of the bulk of a power providing entity that then can smooth out if you've got local solar energy or, from community solar from roofs or, from, solar power plants or whatever will run, that can smooth out the ups and downs and, the fact that the sun doesn't shine at night ever, and, so that's kind of a predictable one. But, and so looking at microgrids and, some of the most robust are internal combustion gensets. They're called generator sets. A lot of times called diesel gensets. But with EPA regulations, you can typically run a diesel genset for 200 hours a year or something like that. In terms of just the amount of NOx that it does put out and CO2 and that kind of thing. So an ammonia genset would be a very interesting, aspect of that. So I started thinking about, the neighborhood energy station then. Actually, just thinking about the BP station that's right around the corner. And, so thinking about a gas station, generally, the biggest tanks underground for the gasoline stations are 25 or 30,000 gallons. And they're filled, typically 2-3 times a week. If you're talking about an underground tank for ammonia, it would be pretty hard actually to cause any kind of disaster with an underground insulated ammonia tank that was chilled, because if you knock the top off of the valve for that, it's kind of already at atmospheric pressure, and the only thing that allows it to boil out is enough heat to get into it. And if it's insulated, it'll kind of sort of come out, and you can smell it, but then you go turn off the valves or whatever. So in terms of safety, if you look at a gas station right now, if you look at my local BP station, which is in the middle of Chicago, there's 16 pumps that are filled up, 18 hours a day, and you probably got 2,000 customer interactions with people that are relatively little trained in terms, they're fairly experienced with it because you buy gas all the time, but not always. If you're teaching your teenager how to drive, they got to learn how to put gas in the car and that kind of thing. But you have, retail interactions. You've got, 3 different grades of product, all kinds of interactions like that with something that was sized that way for ammonia storage for a diesel genset that would run ammonia. I'd just say, okay, well, let's take a 30,000 gallon tank, and let's have a diesel genset there, and we'll have feed in for local solar and wind and that kind of thing, and we'll have a sophisticated which are becoming cheaper and cheaper, basically, power conditioning system, and I'll talk a little bit about that. That allows the introduction of the renewables and the solar and the wind in a relatively straightforward way, and allows control then of the throttling on the engine to do that balancing. And also allows the smart inverters now, in other words, the electronics that takes the direct current that you've basically collected, and then turns it into alternating current. Not only will match your 60 hertz, but does matching of what phase it comes out in and how it matches in the right way, so it doesn't trip up the grid as you feed it in and that kind of. But the point is that there's been a lot learned about how to interface with the grid, interact with the grid, sell power or take power from the grid. That's come into play now, and there are packages and software and that kind of thing that allow that to happen, and so that's something that then becomes something that is much more valuable than the early microgrids would fall off at the drop of a hat from some bump in the system, because they couldn't take any chances with load shedding and things like that, and then had to be very carefully brought back on with phase matching and that kind of thing. These kinds of things can take place automatically and can be done so that you're providing not only power to the grid, but what's called ancillary services and support for sort of larger fluctuations associated with either load shedding or big solar coming in or whatever. So these are things that can actually add to the power of the grid for bringing on more renewables, as opposed to being little ants that are a pain in the butt to the grid. And the other thing is, thinking about it in Chicago, I think about the 40-story, 100-unit condos. CHP is going to be, straightforward there, because hot water heat and space heat and that kind of thing will, be interesting. interesting thing for me for Jefferson County is that you all in Seattle and a lot of the people that think about energy here think a lot about distributing heat and think a lot about distributed heat. Seattle's got a lot of expertise and history in that area, and so in terms of thinking about as you do your kind of planning and strategy and that kind of thing, you've got that in your DNA already. So that's very interesting for something that could do CHP. So, these are the assumptions around, just something that would look like a neighborhood gas station. Stationary IC internal combustion engines. Some of the people in here know what a Sturman engine is, but basically they're, diesel engines. With an installed cost of $700 per kilowatt, which is actually a typical, cost for internal combustion engines now, so that's not, a big change. 45% power efficiency, that's reachable. 40% usable energy beyond that for heat, for combined heat and power. And, these are just things that I put into the model so I could put something in a spreadsheet that came out with numbers, and you can change the numbers and say, well, suppose it's 42% efficient or whatever, and see how much that affects you. But and I talked about the rectifier inverter, so the advanced controllers and power conditioning. And, essentially for that, and, well, I've got ammonia at $250 a ton, and, we can talk as much as you want to about that. I mean, the sales price for ammonia as fertilizer right now is like $600 a ton. But that's because, demand is higher than supply and that kind of thing. If you, the way I think about it is the way I think about the way the LNG industry developed is, you can go to dedicated resources that can only go to this type of, market. LNG was one example of that. So, it was stranded as to otherwise, even if, gas was $8 a million BTU in Texas, in Trinidad, to get the gas to Texas costs a lot of money. So, so you can go to, dedicated resources, build capital as dedicated capital, and, that's the way I think of what the, price could be for this. Now, if you're going to do that, and if you're going to build that ammonia plant, you might want to say, well, I really do want to sell half of it to the fertilizer market because I can make a heck of a lot more money doing that. But if I get the tax breaks and the assurance from the bank and, all that kind of thing, that I can build this plant, if I sell, if I contract to sell half of it at, $350 a ton for, low carbon energy or whatever, then, that's something that can be structured into the project. So that's kind of where that's not my guess at what ammonia price is going to be or is right now or isn't. Honestly, over the last 40 years, the average price of ammonia has been $300 a ton. But, right now it's much more than that. You have to think about sort of where that is and where you might do it in a larger energy economy. But you would have on-site ultra-clean heat and power, conditioned power. With flue gas, you could, basically vent into your living room, and so it could be run in a place like Manhattan or Los Angeles or whatever as well. I've kind of talked through all of this, so but a typical high volume gasoline station, 1.5 million gallons of multiple grades of gasoline or diesel in a year. So what would be something that would look like that from the outside? And, what I've described is something with an underground tank and, kind of a couple of generators would actually look a lot less complex in a BP station, but you wouldn't be able to buy candy bars there, but, it's kind of, the same sort of size. 1.5 megawatt generator, that, there's a lot of assumptions that go into, how big that is, but that would kind of be the right size for, a 100-unit, 40-story condo in Chicago. So, how big a neighborhood here, or, is that going to go to, kind of local grocery stores and a lot of refrigeration or whatever. So, but you can make it a lot smaller too. It doesn't have to be 1.5 megawatts. So, there's lots of options in this. This is just sort of, where I got to. And I have a model of this where you can downsize that and, do all the calculations and that kind of thing. Be very happy to share. General complexity is less. You don't have as many retail interactions. You don't have as much above ground, exposure of valves and, all that kind of thing anyway. Typical tank size is 30,000 gallons. Fuel delivery logistics, 11,500 gallon tank trucks. So, a couple of times a week. Very rough projects cost, $1 million for the ammonia gensets for that level would be actually a fairly, conservative estimate. It'd probably be less than that. And 150,000 for the controller and 150,000 for the underground tank. Then you add in land and that sort of thing. This is just very rough and honestly not very expert guess, but kind of conservative guess of what costs would be. So in general, you're talking about that kind of investment though. And if and as I get into sort of studies with groups that want to do this, like if Jefferson County wants to look at this, then then we'll be working with experts on what does our underground ammonia tank really cost installed and that kind of thing. So that's the stuff that I would go beyond what I do on my desk at home in Chicago. So. And so then this, and obviously I'll provide these slides, and anybody can have them. So this looks just like at the general economics of that, and you can come down to that could be quite a profitable way to do things if you're I forget what the cost of power I was selling it. Cost of power for this is actually above the power cost that you guys are used to. So again, you kind of take that and you can put that in the spreadsheet and then say, well, if it costs 50% more for zero carbon ammonia, what's that costing us on a CO2 basis and that kind of thing. But the point is, we pay a lot for. We don't pay a lot in general in Illinois for power. We pay pretty much for power in Chicago. So, that's based on Chicago prices, not, free power from hydropower. So you guys turn up your noses around here. I say, no, we get it for 2 cents a kilowatt hour. Not much I can do with that. But so that depends on how worried you are about energy security and things like that. Actually the next one might be a little bit better. Well, so this is, just showing a schematic here. It's basically just a diesel engine sitting. You got the exhaust and that kind of thing. You'd have a lot less after treatment for this type of thing. The thing to point out here is one of the things that's done with microgrids now is you take the AC power that comes out of this, and you can take the AC power that comes from wind turbines and all that sort of thing, and put it through what's called a rectifier. So you got AC power that has whatever characteristics in terms of frequency, and you turn it into essentially a straight line. You turn it into DC power, and you don't lose that much efficiency with that. That then becomes sort of the same characteristic as solar PV or batteries or whatever that can be being fed in here to the smart inverter, which then takes your DC power and puts it all together. So if you're getting a lot of solar, you can phase back on the engine or whatever, and turns it back into conditioned power that has the right phase and right frequencies and the right kind of thing to interact with the grid. And again, I'm not an expert on this. It's just the stuff I see that the people that are working on microgrids, talk about now. So that looks very cool to me. The other thing that happens is that if you are running a IC engine directly into a grid, then it has to run at a certain speed, according to what your gearbox does, but it has to run at a certain speed to put out the right even frequency, the right number of jumps per minute or jumps per second. And running an engine at kind of one speed or a set of speeds according to the gearbox takes a lot of the efficiency out of running the engine, because if according to the power curve and according to the frequency or the speed you run it, you can lose a lot of the value and the efficiency of the fuel. Well, if you're running it on this, then you can run at such that the engine is running the most efficient fuel points, because it doesn't matter what that frequency is, it's going through the inverter and that kind of thing. And that becomes something that makes things a lot more efficient, so that helps with CO2 and fuel use and all that stuff. Okay, so this is the same sort of thing that shows, with the smart inverter going out to the AC, you can be feeding in solar here. If you've got in your, either your condos or your industry or whatever, if you got DC loads that you can take out directly, you can feed those. Wind power can come in there to the rectifier. You got heat and cooling that can come out from that, and that would be the generator. So this can be, the point is that obviously you wouldn't design every system exactly like this with all these hookups, but there are very many different options that you can use for a very flexible base here that can allow you to bring in sort of maximum amounts of solar and wind power. I'll get to a couple of the other kind of advantages here. You can easily accommodate solar and wind. You've got kind of a centrally addressable control house for this. So if you had 15 of these megawatt things on the island, the utility could be or whatever you call your local controller and sailor of electricity, could have communication directly to and even control of things that would be strategic to how you handle day-to-day operations for efficiency, or emergency operations if a tree knocks over a line or whatever. So this allows kind of a over time, at least the ecosystem to develop such that you could have kind of distributed power stations that are zero carbon power stations that are taking in distributed energy and that kind of thing. Is there a question?
Yeah, quick question. Sorry, I'm going to have to leave in a minute. But I was wondering, can solar and wind actually create ammonia fuel, or is, when you mention solar and wind, is it just ammonia would be the backup when those aren't operating?
They can create it. So very much like I talked about hydropower for hydrolysis. Anything that you can make electricity with, you can run an electrolyzer that splits water and makes hydrogen. Okay? You can. Now, when you pencil that out and say, right now with the kind of, very sort of kludgy ways that we do that and that kind of thing, it might be sort of a 40% efficiency, of the power into the, the power that you capture in the ammonia, which, may well be not far off of, where it is if you, kludge that together now. It doesn't sound greatly attractive, but it can be attractive even in those kinds of circumstances, depending on where you are. If you're in Africa putting in solar villages and, giving everybody sort of, a light bulb for 3 hours every night and that kind of thing, because you don't have anything to store things in, or the batteries break down or whatever. There are situations where even sort of 30% capture is nice as a, convenient storage solution. It's not the first application I would try to sell to somebody because, it's, but, yes, you can do that. Anything you make electricity with, you can do hydrolysis, so, sure. In terms of storage, so now when, now when you talk about microgrids, you say, how many batteries can we afford to buy to have, to operate our system, before the system comes back for, 3 hours or something like that, because batteries are very expensive to, really store electricity at the grid scale. With ammonia, basically you have stored energy that a megawatt and a half of electricity is quite a lot of electricity. If you got that 30,000 gallon tank and you run that generator, and forget the sort of the advantages of the heat one way or the other, you run that generator, you'll run the generator for 5.5 days on the ammonia you have in the tank. That is 4 orders of magnitude cheaper than doing that with batteries, because batteries are much more expensive. This is a $100,000 tank that gives you whatever it was. I'd calculated 200 megawatt hours of electricity. And, it gets recharged when the truck shows up and puts stuff in the tank. It's not sort of recharging, gee, we got to make sure we get the batteries charged because the sun's shining right now, and, kind of timing on that. So in terms of, energy security and that kind of thing, this is a great solution to that. And, as and if you get to the point where you're taking surplus hydroelectric or, nuclear or whatever to make local ammonia, what's our timing?
You want to get close to being wrapped up in about 5. A lot of people want.
About 5 minutes?
Plan to leave at about
Okay.
fast.
All right. Well, let me finish up then. That's a very important part of this, is actually energy storage and reliability. So that's compared to battery storage, and I already talked about that. So compared to a natural gas genset, so here I'm thinking about, New York and, Pennsylvania gas or whatever. With ammonia, you basically can move the ammonia wherever you want to, because it moves in trains, moves in trucks, it moves on boats and that sort of thing. If you have a TCF of gas under your field in Pennsylvania or whatever, and you want to move that to a big market where it gets more than 50 cents an MCF, then that's a pipeline project. And a pipeline project in New York is a 10-year project that'll probably never get done, because everybody every 5 feet will argue with you about whether they want a pipeline on their field, and it's an extremely expensive project, and has sort of one set of customers at the other end. So in terms of the ways to utilize our gas, or big wind fields, or if you got big hydroelectric areas or whatever, this is a way to move those electrons into something that's storable and movable and fungible, and moves to whichever market's going to pay the most for it. And a lot of what the market's going to pay for in the original stuff is actually just fertilizer, and they're paying a hell of a lot for it in the fertilizer industry. So, but I mean, if you've geared yourself with your credit and the way you got your project set up, if you're making money at $250 a ton of ammonia, then you've probably made some concessions on how much you're going to participate in the fertilizer market or whatever. But you can make kind of utility returns. This is kind of guaranteed, and people have offtake contracts, and be taking their clean fuel and that kind of thing. There's a lot of ways to work out how this would go. but the point is, it's not a 10-year, $3 billion project that, $2.5 billion of it goes to lawyers. And to build a pipeline that's, one set of customers. It's fungible and it moves around, and it's, something that the banks will be a lot happier about and the investors will be a lot more attracted to. This kind of makes the same points. Here I talk about, the kinds of things you might think about, places that need a lot of refrigeration, light industrial. What would you be thinking about for CCHP? In Hawaii they run on diesel and they're paying, 50 cents a million BTU for gas there, and they're paying 40 cents a kilowatt hour. So if you got a resort in Hawaii, then, CCHP would be, you could heat the pool and all that kind of stuff. So, some funny ways to think about it. But so this is just to give an idea of the different ways you could think about the optionality that, ammonia and ammonia energy stations would do for you.
Could you confirm, I think you said we sell electricity out of this for $150 a megawatt? Is that what you said the price was?
Yeah. That was, kind of the base case, assumption, which is high compared to what you're doing here, for no question.
Retailing for like 100.
Well, yeah, and so.
Just trying to make sure I understood what.
Absolutely, yeah. And so when I'm thinking about a base case, I'm thinking about in Hawaii, it's 35 cents. In many places that have hydropower, it's 2 or 3 cents. So, this may not be for everywhere. This is just to, sort of bring that forward in terms of how you can think about it.
Yeah, thank you. I just want to make sure I had the
Yep.
And certainly the values are different when you have an emergency, you need power versus on a day-to-day.
Absolutely. Right.
Thank you. The thing that was interesting me was not so much the use of the ammonia, but what was more intriguing was what would be involved in being a production facility, a production area. Because we have, the single road for transport. So you knock the transport part out if we're a local producer.
Now I'm much louder, but that's true. And so being a local producer, there are many aspects of that would be interesting. Here you also have ports, so you can bring in ammonia, off the water, which, can be, a cost-effective way to do it. But there are many advantages to working on, and there are people that are working on, solar to ammonia. So we have a guy in Iowa. His name is Jay Schmucker, who is a rocket scientist. His father was a farmer in Iowa and had a big farm, and Jay inherited the farm. But Jay actually went to worked at the Jet Propulsion Laboratory for 50 years, which is JPL. It's the place that designs all the Mars rovers and the stuff that goes out past Neptune and shows you the rings and all that kind of thing. Jay worked on that for 50 years, so he's a tremendous engineer and he's got very broad contacts and that kind of thing. And he wanted to come back and use what he refers to as half of his retirement money or whatever, but to build a memorial to his father, which is essentially designing refitting a tractor that can run on ammonia and building a system that makes ammonia run from solar power. So the solar power provides the power to compress the hydrogen and the nitrogen up to pressure and to do the electrolysis and that kind of thing. And that gives a basis for understanding what such a system might look like. And it's not the way that you would build it to make money, but when you get people like this that do things like that, then the engineers can look at that and say, all right, how do we bring down the cost of that if we want to build 100 of those systems or whatever. So there are people that are already working on that, and that's something that we eventually want to do. Definitely.
We've had talks on ammonia combustion in the past, and it seems to me that they said you needed to mix some hydrocarbon with the ammonia to make a stable combustion. Can you burn pure ammonia stably in a conventional combustion engine?
Yes. So there's a guy named, there's another rocket scientist that is running specialty systems that have shown that you can do that. The other, and one way is to add a few percent of diesel or whatever as a combustion enhancer. But the other more convenient way to do it, and the way Toyota is doing it, Toyota has several patents on this as well. So if you have pure ammonia, you can actually take part of that ammonia, heat it up with the exhaust gas from the system and run it over a catalyst that will split it into nitrogen and hydrogen. And you can take that hydrogen, and hydrogen's a very good combustion enhancer. You can take that hydrogen and mix it in with the ammonia to do the same thing, but you don't need two fuels on board. So there are three ways to do it: mixing a little bit of fuel, cracking a little bit of the ammonia to hydrogen, or just some slightly more advanced technologies for doing controlled combustion.
Methane's produced from farms and from landfills.
Could I be talking to the mic, all of you? Maybe
Is it on? Is it on?
Get closer, Rick.
Okay. Methane's produced from a variety of sources. Is there any chemical advantage of translating that to ammonia rather than using it as methane for any of these purposes?
So talking about biodigesters or landfill gas or things like that, those tend to be small enough flows that they don't give you, enough scale to really get to, economic production of ammonia. So that's probably not the best thing. If you had a biodigester on a farm, then using it for pasteurizing the milk or something like that, or local production is probably a lot more useful than trying to turn it into ammonia. Small scale stuff is always expensive, and that's why even renewables to ammonia is expensive as well. It's just the nature of the world that. Basically, it's the nature of geometry, so surface to volume ratio. If you got a small volume that you want to do things, then you got a heck of a lot of surface and a lot of steel to enclose that. The bigger and the bigger you make it, that scales with the cube rather than the square, and so that's why large scale is, and generally inherently cheaper. Hope it's okay if I sit down. I didn't say that.
I was thinking more terms short term. Wouldn't it be better to use renewable fuels to create ammonia for agriculture and then use petroleum fuels for emergency and local power generation?
Well, I would definitely say there can be some optimization and rebalancing on, the amount of ammonia and fertilizer that's used to raise corn that is, in not very environmentally efficient ways turned into fuel that you burn in cars. I think if you saved all that ammonia to actually, sort of run clean power versus, planting and harvesting and, distilling a lot of corn, you might be doing a better job from a point of view. I don't know if that's exactly your point, but there's a lot of rebalancing that can be done that is just mismatches that are caused by regulation, and you know. I'm sorry if that's not politically correct, but I'm not in Iowa, so nobody's going to beat me up about corn ethanol. I was born in Iowa, so I tend to be sort of naturally sensitive about it. But
I was thinking about general fertilizer production, not just for corn. I mean, the corn ethanol one is sort of a...
Well, ammonia has a high value as a fertilizer. It has a high value as a fertilizer here, but around the world has a very high value as a fertilizer, of course. So, you know, if you're thinking, again, as you are from the holistic point of view, if you're able to do solar to ammonia at you know, sort of reasonable cost and scale, it's probably going to be much more valuable in you know, Nigeria or you know, a lot of places where we're putting a lot of solar energy. It's probably going to be more valuable as a fertilizer than, you know, sort of burning it to get another hour on your light bulb. Because in general, the world is, on average, starved for ammonia. Or, you know, could be doing much better if it had ammonia available, put it that way. So, you know, that's exactly the right thing. And the best thing to do with that is let the market set the, you know, the prices. But, again, that's politically incorrect. But, you know, if people are willing to pay $800 a ton for ammonia for fertilizer, you know, you don't want to do too much to try to, you know, dislocate that until you've satisfied that market. And then you can start talking about, well, you know, make the ammonia market, or you make the ammonia supply 10 times as big, the price will come down. Now, the current ammonia players will hate you, and they'll try to put concrete blocks on your shoes and put you at the bottom of Lake Michigan. But because, you know, that ruins their you know, their business model. But you know, the same kinds of, you know, dislocations take place all the time. That's a good question.
Thank you, Steve. Thanks, everybody, for coming.